The afternoon of August 4th, 1943. Inside a dimly lit workshop at the Yokosuka Naval Air Technical Arsenal, south of Tokyo, the air hung thick with the smell of machine oil and humid summer heat, the way every Japanese facility smelled in the third year of the Pacific War. A team of Imperial Navy engineers stood in a semicircle around a workbench, staring at something that should not exist. Before them lay the disassembled remains of an American Pratt and Whitney R-2800 engine, pulled from a downed Grumman F Hellcat near Rabaul just 3 weeks earlier. It had been shipped here under strict secrecy. The engine's 18 cylinders were spread across the bench like the organs of some mechanical beast, each component tagged and photographed. But it was not the engine itself that had stopped the engineers cold. It was a small metal plate, barely larger than a playing card, stamped into the engine's firewall. Lieutenant Commander Yoshiro Tanaka leaned closer, his reading glasses catching the overhead light. The plate read, Manufacturing date, May 7th, 1943. Serial number, R2800-21, Unit 4217. He picked up his notebook and flipped back 3 pages to where he had recorded the aircraft's combat history. The Hellcat had been shot down on July 23rd. Tanaka did the calculation in his head. The number made no sense. 77 days, he said quietly. His assistant, a younger engineer named Kenji Watanabe, looked up from his measurements. Pardon me, sir. This engine was manufactured on May 7th. The aircraft was operational over Rabaul on July 23rd. That is 77 days from factory to combat. Watanabe frowned. That cannot be correct. There must be testing, break-in procedures, installation, transport across an ocean. Tanaka tapped the metal plate with his pen. The Americans stamped the date. They do not lie to themselves. He straightened, his mind racing through implications he did not yet want to voice. If this is true, if they can build engines and deploy them to the Pacific in under 3 months, then everything we believe about American production capacity is wrong. The room fell silent except for the distant sound of metal being worked in another part of the arsenal. Outside, Japan was winning battles. Inside this workshop, these men were beginning to understand they were losing a different kind of war entirely, one they had never been equipped to fight. To understand why a date on a metal plate could shake the foundation of Japan's military confidence, you need to understand the philosophy that had built their aviation industry, and that philosophy began with a single word: mastery. In 1937, when Japanese aircraft companies received orders to expand production for the war in China, the approach was clear. Each engine would be built by skilled craftsmen. Each component would be hand-fitted. Each bearing would be individually lapped until it turned with perfect smoothness. The Nakajima Sakai engine that powered the Zero required 320 hours of skilled labor to complete. Not assembly time, skilled labor, time spent by men who had apprenticed for years, who understood metallurgy, who could feel imperfections with their fingertips. The engine was a work of art. Its tolerances were measured to hundredths of a millimeter. Its cylinders were individually balanced. When it ran, it hummed with a smoothness that spoke of human dedication. Nakajima and Mitsubishi, Japan's 2 largest aircraft engine manufacturers, employed master craftsmen who had trained since they were teenagers. These men did not work on assembly lines. They worked at individual stations, often spending an entire day on a single component. They took pride in their work in a way that connected them to centuries of Japanese craftsmanship, from sword makers to temple carpenters. The philosophy was simple. Perfection took time. Quality could not be rushed. A superior product required superior skill. And for the first 2 years of the war, this philosophy seemed vindicated. Japanese aircraft dominated the skies. The Zero outmaneuvered everything the Allies could field. The quality of Japanese engines was unquestionable. But philosophy, like battle plans, rarely survives contact with industrial mathematics. While Japanese craftsmen were perfecting individual engines, American factories were perfecting something else entirely: the production line. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. In 1941, Pratt and Whitney's East Hartford, Connecticut facility received a contract that would have seemed impossible just years before. Build 10,000 R2800 engines, not over a decade, over 2 years. The company's response was not to hire more craftsmen. It was to eliminate the need for craftsmen entirely. They broke down engine manufacturing into 467 distinct operations. Each operation was studied, timed, and optimized. Each step was assigned to a worker who would perform only that task, over and over, 8 hours a day, 6 days a week. A woman who had never seen an airplane engine in her life would spend her entire shift installing valve springs. She would install 200 valve springs per day. She would become faster at installing valve springs than any craftsman who built entire engines. This was not degradation of skill. It was multiplication of efficiency. By December of 1942, Pratt & Whitney had reduced the manufacturing time for an R2800 from 150 hours to 70 hours. By mid-1943, when Lieutenant Commander Tanaka was staring at that metal plate, they had reduced it further to 41 hours. 41 hours from raw casting to tested combat-ready engine. That number included machining, assembly, testing, inspection, and final approval. It did not include the time to manufacture the raw components, which happened in parallel at dozens of supplier factories. But from the moment the parts arrived at the assembly plant to the moment the engine was crated for shipment, 41 hours. The Japanese had no word for this kind of manufacturing. Their closest term was ryosan, mass production, but that implied quantity without quality. What the Americans had achieved was something different. Quality at quantity. Standardization so precise that parts made in different factories, by different workers, on different machines, fit together perfectly without adjustment. Back in the Yokosuka workshop, Tanaka spent the next 3 days measuring every component of the captured engine. He used micrometers, calipers, and gauge blocks. He checked cylinder bore, bearing clearances, valve stem diameter. Every measurement fell within tolerances of 0.002 inches, 0.002 of an inch. The same precision Japanese craftsmen achieved through hand-fitting, but this engine had not been hand-fitted. The wear patterns on the components, the tool marks, the assembly sequence, everything indicated machine manufacture with minimal hand intervention. Watanabe found something that deepened the mystery. Each major component carried a different manufacturer's code. The cylinders came from a factory in Kansas, the crankshaft from Connecticut, the magnetos from Wisconsin, the supercharger from Illinois. How is this possible, Watanabe asked, that parts from 4 different factories fit together without adjustment? Tanaka had been asking himself the same question. The only answer is that the Americans have standardized their manufacturing to a degree we did not think possible. Every factory must be using identical tooling, identical specifications, identical inspection procedures. He paused, running his fingers along a cylinder barrel. This is not craftsmanship. This is something else. This is industrial discipline on a scale we cannot match. He did not say the rest of what he was thinking. That if the Americans could build engines this quickly, with this precision, then the mathematics of the war had already turned against Japan. That every month they built more engines than Japan could build in a year. That the Zero's elegance was being overwhelmed by sheer mechanical multiplication. That night, Tanaka wrote his preliminary report. He kept the language technical, clinical, but one sentence revealed his understanding of what he had discovered. The R2800 represents not superior engineering, but superior manufacturing philosophy. The Americans have industrialized precision itself. The report reached Naval Aviation Headquarters in Tokyo within a week. It was read, acknowledged, and filed. No immediate action was taken. Because what action could be taken? Japan's industrial capacity was already operating at maximum output. Their factories could not simply adopt American methods. They lacked the machine tools, the standardized gauges, the supplier networks. More fundamentally, they lacked the philosophy. You could not transform a craft-based industry into a mass production system in the middle of a war. The Americans had spent 20 years building their industrial infrastructure. Henry Ford had pioneered assembly line methods in the 1920s. General Motors had perfected supplier networks in the 1930s. By the time war came, American industry was ready to scale. Japan had spent those same 20 years perfecting craftsmanship. Their industry was optimized for quality, not quantity, for limited production of superior products. It was the right philosophy for the wrong war. Across the Pacific, in East Hartford, Connecticut, the production line never stopped. 3 shifts, 24 hours a day. The assembly floor stretched nearly a quarter mile, lit by banks of fluorescent lights that turned night into day. Conveyor systems moved engine subassemblies from station to station. At Station 7, a team installed pistons. At Station 12, another team mounted the supercharger. At Station 19, the engine received its first oil. At Station 24, it was fired for the first time. Each station had a time allocation. Piston installation, 14 minutes. Supercharger mounting, 18 minutes. If a team fell behind, supervisors appeared immediately to identify the bottleneck. But delays were rare. The workers had been trained to perform their specific tasks with machine-like consistency. Many had never worked in manufacturing before the war. Former teachers, shop clerks, farmers. They arrived knowing nothing about aircraft engines. 6 weeks later, they were producing components with tolerances measured in thousandths of an inch. The secret was not individual skill, it was systematic training and specialized tooling. Each worker had jigs, fixtures, and gauges, designed specifically for their task. Installing a piston was not a matter of skill and feel, it was a matter of following 17 specific steps with tools designed to make mistakes impossible. Drop the piston into the jig, compress the rings with the ring compressor, slide the assembly into the cylinder bore until it stops, torque the connecting rod bolts to exactly 75 foot-pounds using a preset torque wrench. Next, the system did not trust human judgment. It eliminated the need for judgment. By Station 28, the engine was complete. It moved to the test cells, where it was bolted to a dynamometer and run for 4 hours at varying power settings. Instruments measured oil pressure, cylinder head temperature, manifold pressure. If anything fell outside specifications, the engine was pulled from the line and sent to diagnostic. 97% passed on the first test. At Station 32, inspectors performed final checks and stamped the approval plate. The plate included the manufacturing date, the serial number, and the inspector's code. If that engine failed in combat, investigators could trace it back to the specific worker who had assembled each component, the specific batch of raw materials, the specific day of manufacture. Accountability was built into the system. Martha Caldwell worked at Station 16, installing cylinder head gaskets. She had been a high school English teacher before the war. Now she installed 36 gaskets per shift, every shift, for 18 months. She could install a gasket set in 9 minutes, 40 seconds. She knew nothing about thermodynamics or combustion theory. She did not need to. Her job was to place 18 gaskets in the correct orientation and torque 108 bolts in the correct sequence. She was very good at it. One afternoon, an Army Air Forces officer visited the plant with a group of military observers. They stopped at Martha's station and watched her work. The officer asked her what she was building. Martha did not look up from her work. "Something that won't quit," she said. That phrase spread through the plant. It became unofficial motto. Not something beautiful, not something perfect, something that won't quit. The philosophy was fundamentally different from Japan's. American engineers did not seek perfection. They sought redundancy. Every critical system in the R2800 was doubled. 2 magnetos, 2 spark plugs per cylinder, 2 oil pumps, twin fuel lines. If one system failed, the backup took over. The engine was designed to forgive damage, to tolerate imperfection, to keep running even when wounded. It was the mechanical embodiment of American industrial thinking. Build it tough, build it redundant, build it fast, build enough that losses do not matter. Back in Japan, Tanaka's team continued their analysis. They tested the captured engine under load, running it on a test stand they had built specifically for American engines. The results confirmed what the measurements had shown. The engine delivered 2,000 horsepower at 2,700 revolutions per minute. It ran smoothly despite having been damaged in combat. One cylinder showed scoring from battle damage, but the engine compensated automatically. The oil system maintained pressure even when they deliberately restricted one of the oil lines. The fuel injection system continued functioning when they blocked half the injectors. It was as if the engine had been designed by someone who expected it to be shot and had planned for it anyway. "This is not how we build engines," Watanabe observed. "We build for optimal performance under perfect conditions. They build for acceptable performance under terrible conditions." "Which philosophy wins a war?" Tanaka replied. "Depends on which conditions actually exist in combat." He was beginning to understand something profound. The Americans were not better engineers. They were engineers who had accepted different constraints. Japanese engines performed beautifully in peacetime testing. American engines performed adequately in combat reality. And combat reality was what mattered. By early August, Tanaka had drafted his complete technical evaluation, 23 pages of measurements, performance data, and manufacturing analysis. But the most important section was just 3 paragraphs at the end. It was the section where he calculated American production capacity based on manufacturing time. If the Americans could build an R-2800 in 41 hours, and if they operated their factories in 3 shifts per day, then a single assembly line could produce 17 engines per day. Pratt and Whitney had multiple assembly lines. Ford had licensed the design and built an entire factory in Michigan dedicated to R-2800 production. By Tanaka's conservative calculation, the Americans were producing at least 1,000 engines per month. 1,000 engines per month. For comparison, Japan's entire aircraft engine industry, both Nakajima and Mitsubishi combined, produced approximately 3,000 engines per month total. All types, all sizes. The Americans were producing 1,000 of a single advanced engine model in the same time Japan produced 3,000 of all types. The mathematics were crushing. Tanaka put down his pen and stared at the numbers he had written. Then he picked up the pen again and added one final sentence to his report. "Industrial capacity, not technical sophistication, will determine the outcome of this war. If current American production rates continue, numerical superiority will overcome qualitative advantages within 18 months. He sealed the report and sent it through military channels to Naval Aviation Command. What he did not know was that his estimate was conservative. By August 1943, Pratt and Whitney and Ford combined were actually producing over 1,300 R-2800 engines per month, and production was still accelerating. The report reached Tokyo in mid-August. It was distributed to senior naval officers and technical staff. It was read, discussed, and filed. Some officers questioned Tanaka's assumptions. Surely the Americans could not maintain such production rates. Surely there were bottlenecks, quality problems, resource constraints. But a few officers, the ones who understood industrial logistics, said nothing. They simply did the mathematics themselves and arrived at the same horrifying conclusion. Admiral Yamamoto had warned before Pearl Harbor that Japan could fight America for 6 months, perhaps a year. After that, American industrial capacity would become overwhelming. He had been right. The war was now 20 months old. The window was closing. But the greater tragedy was not that Japan was losing the industrial race. The greater tragedy was that Japan had never been in the race at all. They had been competing in an entirely different contest, one that valued craftsmanship over capacity, perfection over production, quality over quantity. And the Americans had simply changed the rules of the contest without telling anyone. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. In September 1943, Tanaka received new orders. He was to visit the Nakajima factory in Ota to brief their engineers on American manufacturing methods. The hope was that Japanese industry could adapt some American techniques to increase production without abandoning their quality standards. It was a reasonable hope. It was also futile. The Nakajima factory in Ota was one of Japan's largest industrial complexes, sprawling across acres of workshops, assembly halls, and testing facilities. When Tanaka arrived in late September 1943, the factory was operating at maximum capacity, producing Sakai engines for Zero fighters and Homar engines for the new Nakajima fighters entering service. The factory floor was nothing like an American plant. There were no long assembly lines, no conveyor systems moving engines from station to station. Instead, the floor was divided into individual work areas, each manned by a team of skilled craftsmen. At one station, 3 men worked on a single crankshaft, measuring, fitting, adjusting. At another, an elderly craftsman hand-lapped a bearing surface with abrasive compound, checking his work with a micrometer after each pass. The factory's chief engineer, a man named Hiroshi Yamada, met Tanaka in his office overlooking the main assembly floor. Yamada was 58 years old, a veteran of Japan's aviation industry since the 1920s. He had learned his craft under German instructors and had built engines for everything from civilian transports to the latest Navy fighters. His hands were calloused from decades of work, his fingernails permanently stained with oil. Tanaka spread his report on Yamada's desk, along with photographs of the captured R-2800 engine. Yamada studied them carefully, occasionally picking up a photograph to examine it more closely. When he finally spoke, his voice carried a mixture of respect and skepticism. 41 hours, he said. From start to finish. Tanaka nodded. 41 hours of assembly time. The raw components are manufactured elsewhere, but the final assembly, testing, and approval takes 41 hours. Yamada set down the photograph he was holding. We spent 41 hours just on the crankshaft assembly alone. Our complete engine takes 320 hours of skilled labor. Tanaka had expected this response. That is precisely the point. The Americans have eliminated the need for skilled labor in most operations. They have created tooling and procedures that allow unskilled workers to achieve precision assembly. Yamada's expression hardened. You mean they have eliminated craftsmanship? They have reduced engine building to factory work. There is a difference, Tanaka said quietly, but not the difference you think. He opened his notebook and showed Yamada the measurements he had taken from the American engine. Every tolerance, every specification, matched or exceeded Japanese standards. The Americans are not sacrificing quality. They are achieving quality through different means. Yamada studied the numbers, his frown deepening. He understood what the measurements showed, but something in him resisted the implication. How many inspectors do they employ? He asked. Tanaka had anticipated this question too. According to American manufacturing records that fell into our hands, approximately 30% of their workforce are inspectors. At the Ford plant that manufactures R-2800 engines, 3,000 of the Ford of Prayathas, 15,000 workers are dedicated to quality control. Yamada did a quick calculation. 3,000 inspectors for one factory. We have 200 inspectors for our entire facility. Because your craftsmen do not need supervision, Tanaka replied. They inspect their own work. The American system requires massive oversight precisely because the workers are not craftsmen. But the oversight is systematic. Every component undergoes 70,000 separate inspection checks during manufacture. The system does not trust individuals. It verifies everything. Yamada walked to his window and stared down at the factory floor. Below, craftsmen worked with the careful deliberation of men who took pride in their labor. Each movement was practiced, economical, efficient within its own context. You are asking us to abandon everything we have built, Yamada said. You are asking us to become a different kind of factory. I am not asking anything, Tanaka replied. I am reporting what I observed. But yes, to match American production capacity, Japan would need to fundamentally transform our manufacturing philosophy. And I do not believe we have the time, the resources, or perhaps even the will to do so. Yamada turned back to face him. Then why are you here? To make us feel inadequate? Tanaka shook his head. I am here because a few officers in Tokyo still believe we can adapt, that we can take some American methods and apply them without destroying what makes Japanese manufacturing excellent. I am here because they need to understand why we cannot. Why we cannot, Yamada repeated. Because the American system is not a collection of techniques. It is a complete industrial ecosystem that took them 20 years to develop. Tanaka pulled out another document, this one showing the American supplier network for aircraft engines. He pointed to the diagram. Pratt and Whitney does not make most of their engine components. They coordinate production across 217 supplier factories. Each supplier specializes in one type of component. One factory makes only pistons, another makes only connecting rods, a third makes only valve springs. Each supplier uses standardized gauges, standardized tools, standardized inspection procedures. The parts they produce are interchangeable. An engine can use pistons from Kansas, connecting rods from Ohio, and valve springs from Pennsylvania, and everything fits perfectly. Yamada studied the diagram. We do have suppliers. Tanaka nodded. Yes, but your suppliers are craft workshops, not specialized factories. When they send you a component, your craftsmen must still inspect it, often modify it, fit it to the specific engine they are building. The American system has eliminated that step entirely. But that requires, Yamada paused, calculating, that requires thousands of precision machine tools, all calibrated to the same standards. It requires gauge blocks, inspection equipment, training systems. The investment would be enormous. And we do not have the steel to build the machines, Tanaka said, nor the time to install them. The American industrial infrastructure that makes their production system possible took decades to build. We cannot replicate it in the middle of a war. The room fell silent except for the distant sound of machinery from the factory floor. Finally, Yamada spoke. Then we are discussing a theoretical problem. We cannot change, even if we wanted to. Tanaka closed his notebook. That is the point I need to communicate to Tokyo. The American advantage is not technical, it is infrastructural. They have built an industrial system that we cannot counter with our current resources. We can build better engines. We cannot build more engines, and in this war, more will defeat better. Yamada returned to his desk and sat heavily in his chair. He looked suddenly older, as if the weight of Tanaka's analysis had physically pressed down on him. What do you recommend? He asked. Tanaka hesitated. The honest answer was that he had no recommendations. Japan's industrial path had been set years before the war began. Changing course now was impossible. But he gave the only answer that had any practical value. We focus on what we can do. We continue building the highest quality engines possible. We train our pilots better. We develop tactics that maximize our qualitative advantages, and we hope that quality can hold against quantity long enough for some other factor to change the war's trajectory. It was not a good answer. They both knew it. That night, Tanaka wrote a supplementary report. It was not an official document, just observations he needed to record before they faded from his mind. He described the Nakajima factory, the skilled craftsmen, the pride evident in their work. He noted that in a different kind of war, a war where precision and reliability mattered more than numbers, Japan's approach would have been superior. But this was not that war. He wrote about the fundamental philosophical difference he had observed. Japanese manufacturing was built on the idea that skilled humans, given enough time, could achieve perfection. American manufacturing was built on the idea that imperfect humans, given the right tools and systems, could achieve acceptable precision at scale. The Japanese system optimized for the ideal. The American system optimized for reality. One paragraph from that night's writing would later be found in his papers after the war. I have spent 3 months studying American engines. I have concluded that we are fighting an enemy that understands industrial warfare better than we do. They have not out-engineered us, they have out-systematized us. And against a system, individual excellence is not enough. By October 1943, American factories were producing more than just engines. The production lines extended to complete aircraft. The Grumman plant in Bethpage, New York, was completing one F-6 F Hellcat every single hour, 24 hours per day. The aircraft rolled off the line fully assembled, fueled, armed, and ready for flight. Test pilots flew them directly from the factory to naval air stations, where they were loaded onto carriers. The logistics alone were staggering. Each Hellcat required approximately 6,000 individual parts. Those parts came from more than 800 different suppliers spread across 32 states. Grumman did not manufacture most of these parts. They assembled them. The tail assembly came from one factory, the wings from another, the landing gear from a third, the hydraulic system from a fourth. Everything converged on Bethpage, where, in a choreographed industrial ballet, the parts merged into complete aircraft. The secret was standardization so complete that it became invisible. Every rivet hole was in exactly the same location, every bolt threaded to exactly the same depth, every wire terminated at exactly the same connector. Workers did not need to think. They followed color-coded assembly diagrams that showed exactly where each part went, in exactly what sequence, with exactly what tools. Training time for a new assembly worker was 6 weeks. After that, they were expected to work at full speed. Martha Caldwell, the former English teacher now installing cylinder head gaskets at Pratt and Whitney, had a sister named Dorothy who worked at the Grumman plant. Dorothy's job was installing instrument panels in Hellcat cockpits. She installed 14 panels per shift. Each panel had 63 individual instruments and switches, each instrument connected to specific wiring harnesses, hydraulic lines, or vacuum lines. Dorothy learned the entire installation procedure in 4 weeks. She performed it from memory, the way a pianist plays a familiar piece. The two sisters sometimes met for Sunday dinner. They never discussed what they were building, not because of security, but because the specifics seemed irrelevant. They were building whatever came down the line. That it happened to be instruments for fighter aircraft was almost incidental. They were part of something larger than any individual could comprehend, a continental industrial machine that had transformed American society into a war production system. By early 1944, that system was reaching its full capacity. In January, American factories produced 2,541 aircraft of all types. In February, 2,893. In March, 3,012. The production curve was still rising. Each aircraft needed engines. Each engine needed the R2800 or its equivalent. The engine factories ran continuously, their output limited only by the supply of raw materials and the electrical capacity of their power systems. Japan, by contrast, produced fewer than 2,000 aircraft per month at peak capacity. And peak capacity was becoming harder to maintain as American bombing campaigns began targeting Japanese industrial facilities. The Nakajima factory in Ota that Tanaka had visited was heavily damaged by B-29 raids in February 1945. The Mitsubishi engine plant in Nagoya was hit in March. By April, Japan's monthly aircraft production had fallen to fewer than 800 units. But the real tragedy was not just the bombing. Even without the air raids, Japan's industrial system was approaching collapse. The craft-based manufacturing model depended on skilled workers, and those workers were being drafted for military service or killed in combat. Apprentices could not be trained quickly enough to replace losses. The master craftsmen who remained were exhausted, working 12 or 14-hour days trying to maintain production standards with increasingly inadequate materials. Steel quality declined as Japan's access to high-grade alloys was cut off by American submarines. Aluminum became scarce. Copper disappeared almost entirely, forcing engineers to design electrical systems using inferior materials. Fuel shortages meant engines could not be tested as thoroughly. Quality control suffered not because standards dropped, but because maintaining standards became physically impossible. In March 1945, a Nakajima engineer named Takeshi Sato wrote in his diary about the deteriorating situation. "We are asked to build engines to the same specifications as before, but with half the materials, half the workforce, and no electricity for 3 hours per day. The craftsmen are trying, But you cannot hand-fit a bearing properly when you are too tired to hold the tools steady. You cannot achieve precision when the measuring instruments have not been calibrated in 6 months because the calibration laboratory was destroyed in a bombing raid. The diary was recovered after the war. Its entries documented the slow dissolution of Japan's industrial capacity, not through dramatic failure, but through 1,000 small compromises forced by circumstances. Each compromise was reasonable in isolation. Use slightly lower quality steel because the high grade is unavailable. Accept slightly wider tolerances because the precision grinding machine broke and spare parts cannot be obtained. Train workers in 3 weeks instead of 3 months because there is no time. Each compromise made sense. Together, they represented the collapse of the system. By April 1945, Japanese aircraft engines had an average service life of less than 100 hours before requiring major overhaul. American engines were still rated for 400 hours. The quality gap that had once favored Japan had reversed completely. Lieutenant Commander Tanaka witnessed this decline from his position at the Yokosuka Naval Arsenal. He continued analyzing captured American equipment, continued writing reports that fewer people read. In his private moments, he reflected on the bitter irony. Japan had started the war with some of the finest aircraft engines in the world. They had ended with engines they knew were inferior but could not improve because improvement required resources they no longer possessed. In June 1945, Tanaka was ordered to evacuate Yokosuka ahead of expected American landings. He packed his research materials, his notebooks, his photographs of disassembled American engines. The captured R-2800 was destroyed before evacuation to prevent it from falling back into American hands. Not that it mattered. The Americans had built thousands more. Tanaka's last official report was dated July 28, 1945. It was not about engines or production capacity. It was a simple statement of fact. American industrial capacity has proven decisive. Technical quality has been overcome by numerical superiority. This outcome was predictable from 1943, but organizational momentum prevented effective response. The lesson for future conflicts is clear. Industrial infrastructure determines military capacity more than tactical excellence or individual courage. The war ended 2 weeks later. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.